Hi everyone, it is my pleasure to give a talk at the Video Scene Parsing in the Wild VSPW workshop. I'm LiangChiehChen from Google Research. Today, I will talk about our recent open source library, DLAT2, a modern TensorFlow library for deep labeling. First of all, I would like to thank the contributions from the DLAT2 collaborators. Without their help, we could not have open sourced the library. What is DLAT2? It is a TensorFlow 2 library for deep labeling. It provides a state-of-the-art and easy-to-use TensorFlow codebase for dense pixel prediction. DLAT2 includes all our recent DLAT model variants, allowing the community to reproduce and further improve upon the state-of-the-art systems. The task of image semantic segmentation is to assign a label to every pixel in an image, and the label encodes only semantic class. In the DLAT2 library, we go beyond image semantic segmentation. In particular, we support instance segmentation, where the assigned label encodes both semantic class and instance identity. But the task only works for scene class, such as car and pedestrian. We also support image penalty segmentation, which unifies semantic and instance segmentation. In the bottom, we illustrate the segmentation outputs of each task. Additionally, going beyond image segmentation, we support video panoptic segmentation, whose goal is to assign a label encoding semantic class and a temporary consistent instance identity. In the bottom, we illustrate the segmentation outputs of video frames from the cityscape dataset. As you can see, the cyclist is encoded with the same color, meaning a temporary consistent panoptic label. We also propose a new task called depth-aware video panoptic segmentation, which builds on top of video panoptic segmentation by additionally requiring the visual model to predict the depth of each pixel. In the third column, we illustrate the depth prediction values. Combining all the predictions, we are able to reconstruct the 3D environment as shown in the last column. The DLAT2 library provides more than the original DLAT model series. Specifically, we open source 5 DLAT model variants. The first one is Panoptic DLAT, a simple, fast, and strong bottom-up baseline for image panoptic segmentation. The second one is Axial DLAT. It is a powerful backbone with axial attention layers. The third one is Max DLAT. It is the first fully end-to-end panoptic segmentation model with a math transformer. The fourth one is BIP DLAT. It is a unified model that jointly tackles depth estimation and video panoptic segmentation. The last one is Motion DLAT. It is a simple baseline on the step benchmarks. In today's talk, I will first go through the image segmentation models, followed by the video segmentation models. Our first model, Panoptic DLAT, is a simple yet effective bottom-up approach to image panoptic segmentation. It was the first winning entry of MapleVista panoptic segmentation track at ICCB 2019 Coco plus MapleRay Challenge. At the time of submission, it was also the top 1 method at Cityscape 03 benchmarks. Here is the overview of Panoptic DLAT. We extract dense feature maps with atruse convolution, similar to previous DLAT model series. Panoptic DLAT generates 3 outputs: semantic segmentation, instance center prediction, and instance center regression. The class-agnostic instance segmentation is obtained by grouping predicted foreground pixels to their closest predicted instance centers. We then fuse semantic and instance segmentation by the proposed majority vote to generate the final panoptic segmentation. Our proposed axial DLAT is a standalone axial attention model for image panoptic segmentation. By standalone, we mean only attention layers are used without any convolution operations. The adapted axial attention factorized 2D self-attention into two 1D self-attentions, allowing us to perform attention within a larger or even global region for any feature map resolution. It improves our PMT delay on multiple benchmarks. Non-local block or self-attention operation is able to capture long-range context. However, its computation is extremely expensive. That is the reason why it is usually applied only on top of a network backbone. For example, after ResNet output feature with stride 32. To alleviate the computation complexity, standalone self-attention, SASA, and LRNet propose to compute the self-attention in a local 7x7 region. It enables fully or standalone self-attention models. However, the context range becomes local again. To make the non-local self-attention non-local, we propose the axial attention block. It consists of two axial attention layers, operating along height and width axis sequentially. It ensures both global connection and efficient computation. Another interesting related work is Vision Transformer, which is also a standalone self-attention model by applying patch embedding with a large stride 16. SASA proposed to learn a query-dependent relative positional encoding. It is incorporated into the affinities, generating a dynamic prior of where to look at in the receptive field. We notice that the positional bias only depends on the query pixel. However, the keys could also have information about which location to attend to. We therefore add a key-dependent positional bias. Additionally, we enable the output to also retrieve relative positions besides the content. This yields our position-sensitive axial attention layer, a normal building block that one could stack to form axial attention models for image classification and dance prediction. Our proposed MaxDLab is the first fully end-to-end system for image panoptic segmentation without any hand-designed modules, such as bounding box or thin stuff merging heuristic. At the time of submission, it achieved state-of-the-art performance on the challenging COCO panoptic benchmark. Inspired by Dieter, our model directly predicts a set of non-overlapping masks and their corresponding semantic labels with the mask transformer. Previous approaches to panoptic segmentation adopt a tree of surrogate subtasks. Let's take the state-of-the-art panoptic FPN for an example. It decomposes panoptic segmentation into instance segmentation and semantic segmentation. Building on top of max RCNN, the instance segmentation branch requires box detection and box-based segmentation. The box detection further requires anchor classification and anchor regression. There are a lot of hand-designed priors involved. For example, what is the anchor size? Aspect ratio? How can we design the object centers? What is the non-maximal suppression value? How could we merge the semantic and instance segmentation outputs? On the right, we show a case where state-of-the-art box-free and box-based methods fail. Axial DLab relies on a surrogate subtask of regressing object center offsets. It fails because the centers of the dog and the chair are close to each other. Detectors classifies object bounding boxes instead of masks as a surrogate subtask. It filters out the chair mask because the chair bounding box has a low confidence. On the other hand, our proposed MaxDLab directly outputs the class labeled masks and correctly segments out the dog sitting on the chair. Inspired by the panoptic quality PQ, we propose a PQ-style loss function. It optimizes a dice loss weighted by the class correctness, and optimizes a cross-entropy loss weighted by the mask correctness. The logic behind this loss is intuitive. We want both of the mask and the class to be correct at the same time. For example, if a mask is far off the target, it is a false negative anyway, so we disregard its class. Here is the overview of our mask delay architecture. Instead of stacking a transformer on top of a CNN, we integrate the transformer and the CNN in a dual-path fashion with bidirectional communication between the two paths. Specifically, we augment a 2D pixel-based CNN with a 1D global memory. In the pixel path, we employ a hybrid CNN transformer framework, where low-level stages use convolution operations, while the high-level stages use axial attentions. Finally, similar to conInst and Solo v2, the pixel features is multiplied with the global memory feature to form our mask prediction. The classes of the masks are predicted with another branch of the mask transformer. Our transformer block enables all four possible types of communication between the 2D pixel path CNN and the 1D memory path. First, the traditional memory-to-pixel N2P attention. Second, the memory-to-memory N2M self-attention. Third, the pixel-to-memory P2M feedback attention that allows pixel to read from the memory. Fourth, the pixel-to-pixel P2P self-attention implemented as axial attention blocks. As shown in these slides, max delay could successfully segment out highly occluded objects, while other state-of-the-art approaches fail in these challenging cases of similar bounding boxes or nearby object centers. Our proposed beep delay is a strong baseline for the new challenging task of depth-aware video periodic segmentation. At the time of submission, beep delay achieves state-of-the-art performance on multiple subtasks, including Cityscape BPS, KT mods, and the KT molecular depth estimation benchmarks. Depth-aware video periodic segmentation aims to jointly solve depth estimation and the video periodic segmentation. By doing so, it allows us to restore the 3D information from the perspective image sequences. Let's watch a short video to have a better understanding of the proposed task. Here is the overview of beep delay architecture. It may look complicated at the first glance. In fact, it builds on top of periodic delay by additionally predicting depth estimation and the two-frame instant center regression. Basically, we are performing periodic segmentation on a two-frame input. We also propose a simple yet effective method to stitch video periodic predictions based on mask IOU overlap. We propose to study the video periodic segmentation task from the pixel perspective. Specifically, we propose two new video periodic segmentation datasets, KT step and the most challenging step, together with a new evaluation metric called segmentation and tracking quality, STQ. We also build a simple baseline motion delay for step benchmarks. The Cityscape BPS dataset contains sparse annotations. Only 6 frames out of each clip are annotated. On the other hand, the multi-object tracking and segmentation datasets, KT mods and most challenges, only annotate pedestrians and cars. We therefore extend them by additionally annotating the semantic segmentation, resulting in two new video penalty segmentation datasets, kitty step and the most challenging step. We collect our annotations in a semi-automatic manner. In particular, we employ the state-of-art penalty DLab to generate pseudo semantic labels for each frame. The predicted semantic segmentation is then carefully refined by human annotators. On average, it takes human annotators around 10 minutes to annotate a frame. The refining process is iterated twice to guarantee high-quality per-frame annotations, as well as consistent labels across consecutive video frames. In this slide, we compare cityscape VPS with our kitty step and most challenging step datasets. Our kitty step contains more video frames than cityscape VPS. Even though we only check two classes, they are most dominant classes in a dataset. Our annotated frame rate is higher than cityscape VPS. Additionally, our dataset contains long video frames and long track lengths, which presents a more challenging and practical scenario, requiring both short and long-term segmentation and tracking. In this slide, we show a video demo of our annotated dataset. Before introducing our proposed evaluation metric, let's first discuss the issues with existing metrics. The first issue is that some evaluation scores are unbounded and negative. There's no intuition about what a negative score means. The second issue is that some metrics thresholds true positives based on intersection over union. A minimum threshold of greater than 0.5 IOU is chosen to guarantee unique matching. However, the threshold holding does not align well with human perception. The third issue is that the removal of correct segments gives better scores. In a self-driving scenario, it is critical that correct segmentation predictions are kept, even though they may have a wrong track ID. The fourth issue is that some metrics evaluate tracking on a frame-by-frame basis. The metric should instead work on 4 videos. To avoid the issues mentioned above, we propose to design the metric in the following manners. The scores should be bounded and interpretable. Both segmentation and tracking are pondered equally. The metric should decouple segmentation and tracking errors. We do not want any threshold-based matching, since every pixel counts. Also, the metric should be robust to any post-processing tricks. The better scores should come from a better performance instead of better post-processing. No penalty of correcting mistakes. Both precision and recall matter for tracking and segmentation. We should analyze 4 videos at the pixel level, since it is a segmentation task on videos. Therefore, we propose the evaluation metric, segmentation and tracking quality, STQ. STQ is the geometric mean of association quality, AQ, and the segmentation quality, SQ. This allows us to separately analyze the tracking and the segmentation results. The segmentation quality, SQ, is the widely used mean intersection over union (MIOU) metric. SQ is measured at the pixel level. It ignores tracking IDs and considers both precision and recall. For the association quality, AQ, we use a class-agnostic tracking measure, since semantic errors are already considered in SQ. We use tracking IOU. It works on pixel level and is consistent with SQ. The association quality AQ is defined by the equation shown in the slide. One thing to note is that the true positive associations, with each track's IOU ID score to encourage long-term track consistency. Let's now compare STQ and other metrics, PTQ and VPQ, in a simple illustration. In the illustration, the first row shows ground truth, and the second row shows the prediction. Each ground truth card is in a single frame, where colors encode track IDs. We assume perfect segmentation to highlight the association. In the case of association precision, or ID transfer, STQ is the only metric that properly penalizes ID transfer. In the case of association recall, STQ encourages long-term track consistency. In the case of removal of correct segments, STQ is the only metric that reduces the score. Finally, we propose a simple yet effective baseline called motion delay on step benchmarks. It extends penalty delay to jointly tackle tracking and segmentation by segmenting two frame inputs. To conclude, we introduced delay 2, a modern TensorFlow library for deep labeling. Going beyond semantic segmentation, we are able to perform instance and panoptic segmentation. More than image segmentation, we are able to perform depth-aware video panoptic segmentation. Additionally, the library contains all our recent delay model variants. They achieve state-of-the-art performance on multiple segmentation benchmarks, and the code is available on GitHub. Thank you.